In this short lesson, we're going to complete an ideal gas law problem using the equation PV equals nRT. And we're going to do that using real data obtained right here. Now you'll see currently on the screen a gas pressure sensor. This is basically a barometer. And you'll see on the screen the current pressure. That's atmospheric pressure fluctuating at about 101 kilopascals kPa. That's about 1 atmosphere of pressure, roughly. What I'm going to do here is I'm going to attach this syringe to the pressure sensor, and you might be able to see here that there's about 40 milliliters of gas in the syringe. I'm going to compress that down to 20 milliliters, and we're going to use that as our volume, and we'll read the pressure at 20 milliliters and use this information to figure out ultimately how many moles of gas are being trapped in this syringe. So again, we're going to do an ideal gas law problem using some real data. So let's take a look here. The gas pressure sensor, I'm going to connect that to the syringe. And the pressure in the syringe, as you can see, is still about 101.2 or so kPa. I'm going to compress the gas in the syringe down to 20 milliliters. And notice what happens to the pressure when I do that. There you go. So, that's Boyle's law right there. If we reduce the volume, the pressure increases. I went from 40 all the way down to 20 milliliters, and you can see that the pressure increased to 179 kilopascals. So for the problem, we're going to use 179.8. For the most part, it's fluctuating around 0.8. So we'll go with 179.8 kilopascals of pressure. Likewise, our volume is 20 milliliters, and our temperature right now isn't being recorded here, but I recorded that earlier, and it's about 23 degrees Celsius. So that we'll use as our temperature. Okay, let's try the problem. Okay, so using the data that we collected from the probe on the computer, we're going to go ahead and use the ideal gas law. So remember that the ideal gas law relates pressure, volume, mass in moles, and the temperature of a gas. Mass is now a variable where it was not a variable with Boyle's, Charles, and Gay-Lussac's laws. Now, to do an ideal gas law problem, we need to have 3 of 4 variables. We need to know what they are. So in this problem, our pressure from the probe was 179.8 kPa. Our volume is 20 milliliters. Now, when you do ideal gas law problems, volume should be in liters. The reason why, the R values you've been provided, those are called universal gas constants. The volume on that number is in liters, so your volume needs to be in liters. To change this to liters, we move the decimal 1 to 3 places over to the left, and we end up with 0.02 liters as our volume. So that's what you're going to plug into the equation. What else do we have? N is our unknown. So we're going to solve for the number of moles of gas in the syringe. How many gas particles were in that 20 milliliter, 0.02 liter syringe. R. So again, R is coming from the periodic table. On the back of your periodic table, in the common equation box, you're going to see that one of the boxes is labeled universal gas constant. You're going to choose the R value that matches the pressure units that are in your problem. So here, kPa is our pressure unit. So we're going to choose the R value based on kPa, and that's 8.314. The units for that are liters kPa over degrees Kelvin moles. And what happens is when you do the problem, all the units here cancel out except the unknown unit that you're trying to solve for. In this case, that will be moles. Finally, our temperature, room temperature is 23 degrees 23 degrees Celsius. Now, when we do the ideal gas law, you must use temperature in Kelvin, just like we did with the other gas laws. And that avoids having to divide by 0, or if you had 0 Celsius as a temperature, that would make this entire side of the equation 0, and that just wouldn't work. So to convert 23 plus 273, that gives us a temperature of 296 Kelvin. Okay, so now we're ready to do our problem. We're going to plug in our numbers and we're going to do the calculations. So again, 179.8 times 0.02, and that equals n times 8.314 times 296. So this is our initial setup for the problem. P times V equals n times r times t. Okay? So at this point then it becomes a matter of algebra. N is like x in algebra. We want to get x by itself. Here we want to get n or moles by itself. So to do that, you're going to follow order of operations. So we're going to multiply first. You're going to multiply these two numbers, and then you're going to multiply these two numbers. So we'll simplify by multiplying these two numbers and then multiplying these two numbers. When we do that, we get 3.596, and that equals n times 2,460.944. We'll round once we finish the problem. Next, we'll do division. So to get n by itself, you should divide both sides of the equation, both sides of the equal sign, by 2460. So we'll do that now. 2460.944, 2460.944. So then obviously this cancels out here, and n equals 3.596 divided by 2,460.944. So n, the number of moles of gas in our 20 milliliter syringe, or in our 20 milliliters in the syringe, and there's our syringe again. Hey, I'm back. So how many moles of gas do we have in there? Well, when you do the math, you get 0.0015 moles of gas. And I rounded there to reflect our least number of significant figures, which is the 20 in our volume, in our initial volume, as well as the temperature, sig figs. So 0.0015 moles of gas is our final, or is our mass in the syringe. And that's basically how you use the ideal gas law. You'll use the same technique to find any of these variables if they're the unknown, and you simply plug in the numbers you do know and then solve for x. Get the unknown by itself algebraically to figure out what its value is. Okay?